Good morning everyone. Today let's start our third semester topic. In this semester I will be dealing with the module Structural Inorganic Chemistry, Units 1 and 2. Let's begin with Unit 1, Solid State Chemistry. So let me introduce you the syllabus. First part of the syllabus deals with structure of solids. In this part, we have to discuss about imperfections in solids, types of imperfections like point defect, line defect and plane defects, structure of certain compounds like zinc blende, quartzite, rutile, fluorite, antifluorite, nickel arsenide, perovskite and ilmenite structures. Structures of spinels and inverse spinels also have to be discussed. Let us begin with imperfections in solids. You might have learned solid state chemistry in the UG level and you know what a crystal is. In a crystal, atoms, molecules or ions are arranged in perfectly ordered manner in the three-dimensional crystal lattice. So now we are talking about a perfect or ideal crystal in which all the entities of a crystal are placed at lattice points, giving rise to a three-dimensional crystal lattice of a perfect crystal. Is it so in the case of real crystals? Real crystals are like us, human beings. They are never perfect. They are always associated with some defects or imperfections. So what is a crystal defect? It can be defined as any deviation from the perfect atomic arrangement in a crystal. A crystal defect is any deviation from the perfect atomic arrangement in a crystal. It is a lattice irregularity that can be of any dimensionality like one-dimensional, two-dimensional or three-dimensional defects. So in nutshell we can say the crystal defect or imperfection is a lattice irregularity or a deviation from the perfect atomic arrangement. As we have just discussed now, an ideal structure of a solid means when every lattice point has exactly the same environment. Any deviation from this ideal structure can be termed as a defect or an imperfection. We have seen what is a crystal defect or imperfection. Then why do we study about it? Why is it important? It is because the properties of crystalline materials are greatly controlled by the extent of imperfections within that crystal. The properties of a crystalline material is controlled by the extent of defect or imperfection within the bulk of that crystal. Properties like electrical conductivity, mechanical properties like strength, toughness, hardness, etc. and also optical properties, magnetic properties and kinetic properties like diffusion. All these properties of solid materials can be controlled by the extent of imperfection. So crystal defects, are they good or bad? It's a good question, right? In fact, they are necessary or even crucial for the behavior of crystals that can be employed in many fields of technology. All technology involving materials depend on crystal defects. For example, formation of alloys, where we are adding imperfections to the solid. Mechanical and magnetic properties can be induced by introducing defects in crystals. So together with the basic nature of crystals, impurities also play a vital part in controlling the properties of a solid state material. So it is not just the original crystal controls the properties of the material. Together with that, the presence of impurities or imperfections or crystal defects also controls the properties of solid crystalline materials. So now we know imperfections can control properties of crystals. They affect the physical, chemical, mechanical and electronic properties. Now let us see some examples. Conductivity of semiconductors. Through doping, we introduce some impurities that creates defects leading to the formation of p-type and n-type semiconductors. Imperfections are the reason for color and luminescence of many crystals. You might have heard about F-centers, which is the reason for the pale yellow color of sodium chloride crystal when heated in presence of sodium vapor. Impurities or imperfections accelerate atomic diffusion, especially when lattice vacancies are present. We will be discussing about it later. Similarly, mechanical and plastic properties are also controlled by imperfections. Imperfections in crystals can be of different types. Point defects, that is confined to the vicinity of few atoms or at a single lattice point. So it is a zero-dimensional defect. So point defect is a type of defect that is confined to the vicinity of few atoms or at a single lattice point, and it is a zero-dimensional defect. The other type of crystal defect is line defect that extends along a row of atoms. So it is a one-dimensional defect. And then we have planar defects that extends along two-dimensional surface. So it is a two-dimensional defect. Then three-dimensional defects such as volume defects may also occur. So once again, defects in solids can be point defects or point imperfections which are zero-dimensional, line imperfections or line defects which are one-dimensional, then plane defects or surface defects which are two-dimensional, and volume imperfections spreading to three-dimensional space. Now let's have a look into the different ways in which Fawcett crystal defects are classified. Point defects can be of different types like vacancy defects, Schottky defect, self-interstitial defect, Frenkel defect, color centers, polarons and excitons. And we will be discussing about some of them in detail. And the one-dimensional defect, line defect, may occur in two types, edge dislocation and screw dislocation. And the two-dimensional defect, surface defect, can be of four different types: grain boundaries, tilt boundaries, twin boundaries, stoking faults. And the three-dimensional volume defect can be of the type inclusions or voids. So till now we have seen what are crystal or solid imperfections. Thank you.